Here we consider the pace of radiations. Are they explosive or drawn-out affairs? This question is relevant to the underlying mechanisms of an increase in Earth's biological diversity. Fast radiations may reflect fairly quick response to changed conditions, a mass extinction, for instance, that clears ecological space for something new. A slow, stately ramp-up in diversity, in contrast, may reflect how animal groups come to utilize key innovations that give them an opening to diversify. The fossil record shows us that many animal diversifications begin with small, inconspicuous, and oftentimes somewhat generalized ancestors, long before any explosion in biodiversity, body sizes, and ecological innovations. For instance, the Metazoans start maybe 1 billion years ago with multicellular animals, become visible to paleontologists as sponge biomarkers 700 million years ago, and finally radiate into diverse and large animals of the Ediacaran world and the Cambrian about 400 million years after their birth. Sepkoski's modern fauna is like this too. Groups like fish, bivalves, and cephalopods get their start right at the basal Cambrian, but it takes the Permo-Triassic mass extinction and perhaps a jump into the oxygenation of Earth before these groups take off 300 million years after their births. The pattern is even more acute if we take molecular clock data into account, nearly all of which suggests that animal and plant origins are perhaps 100 million years earlier than suggested by fossils. Paleontologists have described these trends of early, low-diversity, low-complexity origins of animals and plants as the long fuse model. The fuse is lit tens or hundreds of millions of years earlier than the eventual explosion. The idea of a slow lead-up to irradiation is countered by direct fossil evidence that the explosion sometimes seems to come hot on the heels of the fuse being lit in the first place, namely that sometimes we're dealing with short fuse radiations. Particularly when mass extinctions set up a subsequent diversification, the record looks a lot like short fuses dominate. But do they? Let's start with a look at the mammalian radiation after the dinosaurs are bumped off during the end Cretaceous mass extinction. Mammals come into their own after the KPG mass extinction. We find 23 species of placental mammals at or just before the Cretaceous-Paleogene boundary. This figure balloons to 60 species 5 million years later. Ecologically, most of these Paleocene mammals are small and insectivorous. Many are built along the condylarth design, with short legs, a barrel-shaped body, and fat storage and a thick tail. They look a lot like Tasmanian devils today. By early Eocene, nearly all modern crown groups have appeared, such as the bats, horses, primates, and rhinos. Africa gets first elephants. South America has a marsupial fauna in common with Antarctica and Australia. During the radiation, body size rapidly increases from 2 pounds to sizes of pretty big animals today, about a ton, within 5 million years after the extinction. All of this is consistent with the short fuse model of diversification. The dinosaurs died, and the mammals exploded into the vacated world. But there are 3 lines of evidence supporting the rival long fuse model. First, molecular clocks say that most major orders of mammals have Cretaceous origins. Indeed, maximum diversification rates of mammals, as seen in rates of genetic evolution, occurs between 75 and 85 million years ago, even though the dinosaurs are still doing very well then. This genetic analysis by Meredith et al. 2011 suggests that mammals separated into groups that later became cows, primates, and bats, well before any of them looked like their modern descendants. Second, increasingly the Mesozoic mammalian fossil record is getting better too, showing us that stem group mammals are diverse both taxonomically and ecologically. And third, frankly to everybody's surprise, the mammalian radiation after the Cretaceous-Paleogene mass extinction is not seen really at all in rates of molecular evolution. That finding suggests that the radiation occurred in already established groups back in the Cretaceous. Mammals just got bigger and ecologically diversified in the Paleocene, but their genes did not diversify very much. Apparently, becoming big and ecologically distinctive does not require much in the way of new genes. So it sure looks like the mammalian radiation got going in the Cretaceous with the appearance of all the modern mammalian orders while they were still generalized small animals that are nonetheless ecologically diverse. The long fuse model has some life in it yet. On top of the mammal data, we also see that insects and birds radiate in the late Cretaceous too. A bunch of the Mesozoic birds radiate a lot into forest habitats and have their own back-to-the-ocean radiation into marine species feeding on fish. Most of these are taken out in the subsequent mass extinction, leaving survivors amongst the ground birds like ostriches and chickens. But Cretaceous birds are still a diverse lot. Finally, it turns out that armored dinosaurs like the ceratopsians and hadrosaurs, as well as the theropods, all radiated in the late Cretaceous as well. All these radiations suggest that mammals, insects, birds, and even dinosaurs diversify because flowering plants expand the available habitat over the previous gymnosperm-dominated ecosystems. Flowering trees not only have more easily digested leaves than gymnosperms, but they also have fruits and nectar and extensive coevolution with insect pollinators. Angiosperms not only create great resources for insects, but insect abundance also enlarges the resource base for birds and mammals. The mammalian long fuse has been controversial for a long time because we focused on the explosion of body sizes and crown groups in the Eocene as the real action, while remaining ignorant of its roots. The Mesozoic mammal radiation is still pretty poorly known, even though it's getting better every day. Fortunately, we still have some other fossil groups that are much better documented and show the nature of long fuse processes better even than the mammals. Here I'm talking about my first love, the planktonic foraminifera radiation of the Cenozoic. The Neogene globorotalids, a group of planktonic forams, start from small globular ancestors that are classic generalized stem groups. There are multiple lineages in the Oligocene, say 25 million years ago, that all look like pieces of popcorn, globular shells without much distinctive ornamentation. About 15 or 20 million years ago, these clearly separated into 5 different clades. Each clade goes on to evolve distinctive ornamented forms that are broadly convergent, but not exactly convergent on each other. Each group is distinguished by details of their shapes and their biogeography, since some are characteristically tropical, others are subtropical, and still others are temperate. In the foraminifera, the fossil record is very good with excellent time control. We also have drill cores all over the world's oceans and commonly excellent fossil preservation. Foraminifera literally make the sediment they're found in, so abundance is no problem either. So there's no question that the stem groups are real things that predate the more specialized and biogeographically restricted crown group foraminifera. In foraminifera, we can literally watch as generalized stem groups split and give rise to more distinctive crown groups. We can see the fuse burning. If mammals and foraminifera are a guide, genetic diversification can happen at small body size and in generalized morphologies. Much of the heavy lifting of creating basic new biodiversity happens by exploration of what is possible with a new body plan or a key innovation. In essence, the plans are all laid well before they're put into effect. There can still be triggers, of course, that allow an explosive phase of diversification to occur, like the dinosaur extinction that allows those differentiated mammal groups to become large and even more distinctive. But I wonder if the mammals would have diversified so fast in the extinction's aftermath if the genetic radiation had not already happened.